Testing individual inputs using methods like boundary value analysis works well for isolated variables. But when software relies on multiple interacting conditions, testing only the edges leaves gaps in your coverage. Overloading software with nested if-then-else statements makes tracking logic paths difficult. Without visual structure, bugs remain hidden inside these interactions. To manage this, we use two distinct black box frameworks: decision tables for combinations and graph-based models to map sequences. Translating requirements into these visual models forces a structured approach, preventing the number of possible test cases from spiraling out of control. A decision table is divided into four main quadrants. We reserve the top left for the input conditions and the bottom left for the resulting actions that the system must perform. Let's apply this to a print shop system where customers are assigned tiers based on volume. We place those states, regular, silver, and gold, directly into the conditions quadrant. Next, we define the perks. The system can apply a normal rate, an 8% discount, or place the order in a priority queue. These are listed in the actions quadrant. Now we build the logic. Pause the video for a moment. Look at the matrix on the right and predict how the column for a silver customer tier should be mapped. To build the column, we flag the silver condition as true. Then we move down the list and set the corresponding actions, the discount and the priority queue, to true as well. Once the matrix is filled, each vertical column represents a specific processing rule, linking a combination of inputs to its required outcomes. This isolated vertical rule translates directly into one executable test case. For a silver customer, the tester verifies that both the discount and the priority queue are triggered. While tables handle logic at a single moment, software often operates in phases. To track state changes and sequential operations over time, we use graph-based methods. This airline reservation flow uses a specific visual grammar. The circles, or nodes, represent data objects or system states. The lines connecting them, the links, represent the relationships or transitions between those nodes. To test this model, you start at an entry point and physically travel along the links, moving from node to node until the sequence is complete. Completing an unbroken path through the graph creates a discrete test case. Every node and link along that path becomes a verified step in your testing sequence. Graph traversal ensures that functional relationships work in the correct order. This allows you to catch errors in the workflow itself, rather than just testing isolated logic. In large-scale systems, these two methods are often used together to ensure thorough coverage. This graphic shows how they scale. A single node in a system-wide graph might represent a complex calculation that requires its own decision table to test every internal logic path. To summarize, for tables, list your actions and conditions, then map them into columns. For graph-based testing, nodes represent states, and links represent their relationships. Ultimately, these frameworks are tools for systematic extraction. They allow a software team to design a set of tests that effectively probes errors, while confirming the system meets its functional requirements.